What's up everyone, and welcome back to another video. Today we are going to be covering Cramer's rule. Cramer's rule is a way to solve for a system of equations, or a system of linear equations. So let's just say we are given a matrix A which is non-singular and square. That means it has more than one column and more than one row. We're also given X and B. X is a vector of what we're trying to solve for, and B is a vector of our constants. So this is the formula for Cramer's rule, or the system, how it can be written: AX equals B. So to solve for Cramer's rule, we are going to find the determinant of A. So if you've never found a determinant before, what you do is you make a matrix. Let's say we have a 2x2 matrix, A, B, C, and D. We would multiply A by D and subtract that by the product of B and C. If we were to make this a 3x3 matrix and add E and F, we would then multiply A by the difference of the products of B and F subtracted by the product of E and D. So we take this first value multiplied by the square matrix, the determinant of this square matrix. Then we subtract it by B and the product of the difference of the determinant of these two values and these two values. So A times F subtracted by E times C. Finally, we're going to go to our last column, E, and take the product of that multiplied by the difference of A, D, and B, C. So we're going to add this last value, and this will be E multiplied by A and D and B and C. So for a 4x4 matrix, what you would do is so let's say we were to go 4x4. We added values here, 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 here. So we'll just toss in x's. We will erase this. So to solve for this, you would just take A and find the determinant of this 3x3 matrix under B, E, and X. Then we take B and find the determinant of multiplied by the determinant of C, X, X, F, X, 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 X. Then we do E multiplied by the determinant of C, D, X under, and then for X we take C, D, F under, and multiply that determinant by X. So it would be A minus B plus E minus X, and you take the determinants of their respective, we'll call counter matrices. So that's how you find the determinant of A. To find the determinant of AI, what we do is, this is just going to be us substituting this B vector into our column. So for A1, A12, A13, A1n, when we repeat this on the first iteration. When we repeat this on the second iteration, we're going to be replacing all the values in the second row with this vector B. Then we'll do the same thing for the third row, then the fourth, until we reach n. And every time we replace that row with B, we're going to take a determinant, and we're going to solve for x1, x2, x3 up to xn. So just to reiterate that, the determinant of A is simply just solving for this, the determinant of this matrix as is. AI is going to be B substituted into whatever iteration of that row. So the first iteration, first time we're repeating this, we'll replace the first row. Second time we'll replace the second row with B. Third time we'll replace the third row with B. Fourth time we'll replace the fourth row with B. So it's B1, B2, B3, Bn. And then every time we replace these values, we're going to take a determinant, which will be A1's determinant. So A1's determinant would be this row replaced by these values, and this entire matrix is determinant after replacing that first row. So that would be A1. A2 would be the same process, but here. So us replacing this second row would be, and then taking the determinant of this new matrix, which we're going to call A2. So what does x tell us? If x is equal to, if the determinant of A is equal to 0, then our matrix is has either infinite solutions or no solutions. If our determinant, or the determinant of A, is not equal to 0, then our matrix or system of equations has a unique solution to it, and it's consistent. So here are the three rules, just written more formally. If the determinant of A is not equal to 0, then the system is consistent and has a unique solution, which is given by that formula that we just went through. If the determinant of A is equal to 0 and at least one of the determinants of AI is not equal to 0, then the system is inconsistent. It has no solution. If the determinant of A and all of the determinants of AI are equal to 0, then the system is consistent and has infinite number of solutions. So our goal is just to see if this determinant of A is not equal to 0. And if it isn't equal to 0, then we're going to be looking to solve for it, find the unique solution. So, awesome. So here's a Python code that I ran across that I liked. It uses this library SymPy, which is good for symbolic math. It's good with matrices, dealing with matrices. So we're going to skip this line over here. We don't need to add symbols. We're going to create matrices A and B. So we'll be doing this. We're going to be calculating the determinant. We're going to follow. So here we have A, 1, 2, 3, 4, 5, and then we also have a lot of repetition from up to over here. We're going to create this or compress this into a for loop so that it's just repeating for I number of iterations, as we saw here, I. And awesome. So shouldn't be too much, maybe 20, 30 lines of code. We will get this done. So we're going to start off by importing from SymPy. From SymPy, import matrix. We're going to be following an object-oriented programming during this project, so we'll try to make it everything follow a single responsibility, just spread everything out. Awesome. So let's do class equals Cramer's rule, and class Cramer's rule. We're going to define init. Let's go self. We're going to do self.a is equal to a. So we're going to need a as a parameter. We're also going to need b. So self.b will be equal to b, and we will have self.a or I equal to a.columns. So for SymPy, it's COLS, not columns like this. If you do columns, if you type out the word columns, you'll get an error, so you want to do COLS. Next, we're going to define. So we want every function to just focus on one thing. We want it to be simple. We're gonna have to check for the determinant of A, right? That's the first thing we're doing here. That tells us whether our system is consistent or inconsistent, whether it has a unique solution, an infinite solution, or no solutions. So let's do define determinant. What can we name this? We'll just name this determinant or solver checker. We're going to call this checker. Checker, awesome. We're going to return this is self.a.determinant, and we will do does not equal 0. So we want to check if this does not equal 0. When we do return and then do self.a.determinant does not equal 0, this is going to return a binary variable, either true or false. So we're going to check for that in our next function. Solver, checker, and solver. Cramer's rule, we're going to have a checker and a solver. So the solver is going to check. The checker is going to check if the determinant of A is not equal to 0, which means that there's a unique solution. So if not, we want to check if this is not equal. So we got if self.checker. If self.checker, we just do self.checker. So if self.checker, self.checker, let's do so what we're going to do is, first step, we have ax, we want the determinant of a. Let's get a determinant of a equals self.a.determinant. Awesome. So if self.checker determinant of a, so now that we got the determinant of a, we already know that this is not equal to 0. So what we could do is self.for we're going to change this to column, self.column, and we're going to make this for I in range self.column. So this should loop through all the columns, and what we're going to do is take AI. I like this better. So I'm going to do AI, and we're going to make this equal to take a copy. Let's take a copy of A. Then we're going to do A.I, and we're going to do, let's access the I, the row, and we're going to say this is equal to self.b, right? Self.b, capital B. Awesome. So now what we're going to do is determinant of I equals self dot, we don't need self, we just need AI dot determinant. And so what we're going to do is we're going to do we need a list, since we're looping through this. We're going to do solution, or we'll do x equals, this is going to be an empty list. X is going to be an empty list. We're going to do determinant of A, or determinant of I. Determinant of I equals AI determinant. xi equals, this is equal to the determinant of A divided by the determinant, the determinant of I divided by the determinant of A. And we're going to take x dot append and put xi. So let's do our else. So if both are equal to 0, right, then there's infinite number of solutions. So when we do an if, we're going to else, because then there's only two cases, true or false. So we're going to do else, and we'll do another if in here. So else if determinant of A does not equal 0, or no. What we have to do is for I in I in range self dot column AI equals self dot A dot copy. Place this I row with self dot B, that B vector. Then we're going to go follow the same steps. So we want to follow the same steps, and then we're going to end it off by calculating our x. Then we're going to append this I, and we're going to say, so let's actually move this. You need to do this twice. Why are we doing this twice? This is wrong. So let's do this. Let's keep this. These are, I get better function names. Alright. So we are going to put our code over here. Define solver self. What if we do if determinant, we're going to name this solver, we'll just name checker. Just name this matrix calculator, and I'll name this last one solver. So let's go if solve.matrix calculator x here. Let's do if self.matrix calculator if checker, if self.checker. So if this is true, it's equal to 0. We'll do matrix calculator self.matrix calculator. So we got our matrix calculator. We calculated the determinant of x, right? So be good actually. Print for I in self.x. So we're just printing results here. For I that's in self.x, print. We'll do printf and do x xi equals this is not we're gonna have that let's do n equals 1. Make this n and we'll just have this iterate through. We'll do n equals plus 1. Awesome. So n plus equals 1. Let's do our else. So if we don't have a unique solution, what happens? We're going to check if self.matrix calculator self.matrix calculator, and let's do infinite solution. So we're going to check if is consistent and has. So is consistent and has infinite solutions. Else self.matrix calculator. So if this is false, it's not. If it's equal to 0 and AI, it's matrix. System is inconsistent and has no solution. Awesome. So what we're going to do is we're going to try running this. We're going to take that matrix that we saw in there. A is equal to matrix. Comma minus 4. So the difference between SymPy and NumPy and alpha is that NumPy, when you create an array, if you're creating a matrix, you have to use 2 brackets, versus in SymPy you only use 1 bracket and the parentheses. Oh wait, actually we are using 2 brackets here. So we're using 2 brackets here. So that's not a difference. That's actually nice. I like the way that they formatted this in here. Cool. So 2, 3, minus 4, 5, 6. Awesome. 1, comma, minus 2, 3, minus 5. So let's go 3, 1, 2, 4, minus 1, 2, comma, minus 3, 4, comma, 1, comma, 5, 4, 2, 3, minus 1, 2. Perfect. Now let's get our matrix for B. It's going to be 10. We're going to have 10, 20, 15, 25, 30. Cool. So here is, I'm just going to run through this just to make sure that I'm not missing anything. So we have our checker, so that's not on here, but we have a self a determinant. Awesome. Self.a.copy, self.b, perfect. Determinant of a, what do they call it? A1, A2, A3. So AI, that's a cool. Determinant of AI. I like the code. Printf. They just wrote out manually. So let's solve this. Let's see what happens. We have, we're gonna call this B. Just the object got returned. object equals solution dot checker. Just do calc equals solution dot matrix calculator, and then we're going to do solve equals solution dot solver. Awesome. Now let's print check first. So what happened here? Solution solver. So no object X. How do I get this? Make a list global. Stay away from that for right now. Let's go. Try this, but Cramer's rule object has no attribute. So, what is this doing right here? So let's try this now. Okay. We got I printing here, so we need this to be dynamic. It's true. And true. Then we're getting so we're getting this. We're getting the true with self.checker here. And we're in the calculations. So what if let's actually check this. see how the results are. So theirs only has 5, so something is messed up here. 425 over 62, 6. So the math is done right, it's just being doubled for some reason. Maybe it just got added twice in here. Or it being printed twice, that is it. So it's just being printed twice. We will yeah, it's just being printed twice, so we don't need this. Awesome, perfect. So now we solve for this. So that's how to code Cramer's rule in Python. Let's just make sure that this is going to code Cramer's rule with infinite solution. And, system with infinite equations. I think we found one. It's going to be 3. So let's make our new matrix. It's going to be 2, 4, minus 6. This is courtesy of geeksforgeeks.org/Cramer's rule. 3, 6, minus 9. And let's do 4, comma, minus 7, comma 1. Our B is going to be 19, 30, 15. System is inconsistent and has no solution. What if we were to flip this? Let's just make sure that this... Awesome, so this works. So now we completed Cramer's rule. Let's see if we have one that is infinite. So we're gonna actually take all of these down as test cases so that we can add unit test in here. We already have this one taken out, so we'll copy this, Control Z. This will add the B, which was 30, 15. To put a hashtag, or yeah, we'll make this condense this into one line just to make it easier. So awesome. So we are going to end this video here. We'll call this part 1. We're going to have 2 more parts to this. The next will be adding unit tests to just assert that the program is running well. And the third will be deploying this with Flask or Fast API. Actually, yeah, we're going to use Flask. So we'll deploy this with Flask. We'll use, so yeah, thank you guys for watching. If you enjoyed, please stay tuned. We'll have more videos. And yeah, thank you guys. Have a great day.